In this video, I will show you how to integrate a variety of quotients. I have grouped the problems into sets of problems with very small differences, so we can compare and see how the small changes show up in the answer. Usually, when we are given a quotient like the one we see in problem A, we have to decide whether or not we will use inverse trig rules. However, we are told right from the start that we are going to be using arctangent for this first set of problems. But I still wanted to mention that in general, we look at the degree of the numerator and compare it to the degree of the denominator. If the degree of the denominator wins by 2 or more, that's how we know that we will need inverse trig rules. And that's the case here. These are the 3 inverse trig rules that you need to memorize. But we already know we need to use arctangent, so let's get it. Part A is a perfect match for the arctangent rule. So let's just jump in, noticing that the A value is 1. The A value is always the square root of this constant. So the rule says 1 over A. Well, that's 1 over 1, so we don't need to write that. Let's just go ahead and write arctangent U over A, well that's just x over 1, which is x, plus c. So that's your answer to part A. Comparing with part B, the only difference is we see this 9 in the numerator. But we can just bring that 9 out in front of the integral, and that will leave behind 1 over 1 plus x squared dx. This integral is the same as what we had before. So just applying the rule once again, we have arctangent x plus c, but the 9 that we brought out to the front will now appear in the front of the answer. For part C, we see the 9 as the constant in the denominator. That will change the value of a. A is always the square root of this constant, so a is 3. Looking at the rule, we have 1 over a in the very front. So we will now have 1 over 3 in the front. And then arctangent of u over a. So in this case, that'll just be x over 3 plus c. For part D, we have a 9 in the numerator and as the constant of the denominator. So we can bring this 9 out in front of the integral, as we saw before. That will leave behind 1 over 9 plus x squared dx. This integral is still a perfect match for the rule. The a value will again be 3, which is the square root of this 9. So we can go ahead and begin to write the answer, which will be 1 over a. So we will have 1 over 3. Arctangent u over a, which in this case is just x over 3, plus c. Don't forget about the 9 in the front. 9 times 1/3 is 3. It's the same as 9 divided by 3. So here's your final answer for part D. For the second set of problems, we are told that these will all be arc-sine rule problems. But we could have guessed that because we see the square root which appears in the arcsine rule, and we see that we have the constant minus the variable. And that's how it shows up in the rule, the constant minus the variable. So we would have known anyway. This first one is a perfect match for the rule itself. Just keep in mind that the a value will be 1 because it is the square root of this constant. Notice that the arcsine rule does not have 1 over a in the front. So we just jump right in and write arcsine. U over a will just be x over 1, which is just x, and then plus c. Comparing with part B, we see the 16 in the numerator instead of the 1. We will bring the 16 out in front of the integral, leaving behind 1 over the square root of 1 minus x squared dx. So we now have the exact same expression that we had in part A, just with a 16 in front of it. So guess what? We will have the exact same answer as part A, arc sine x plus c, just with a 16 in front of it. In part C, we see that the 16 has now jumped down to become the constant in the denominator. That will make the a value equal 4, because the a value is always the square root of this constant. Other than that, this is still the same situation we were in before. So looking at the rule, there is no 1 over a in front. So we can go ahead and write arc sine, but u over a will now be x over 4 plus c. Looking at part D, we see the 16 in the numerator and as the constant in the denominator. The 16 from the numerator will come out in front of the integral, and we will have 1 over the square root of 16 minus x squared dx. Then we will understand that the a value is equal to 4, because the square root of 16 is 4. And we begin to use the rule. This rule has no 1 over a in front, don't forget that. So we begin writing arc sine u over a, so that's x over 4 plus c. But because we have the 16 in the front, the 16 will appear in the front. Kabam! For the third set of problems, we are told that we will be using the Arc Secant Rule. However, we knew that because in the problems that we see, we have the variable minus the constant under the radical, and here we have the variable minus the constant. Also, the rule has this extra variable out in the front, and these problems do have this x out in the front. So let's see what's happening. In this case, it's just a perfect match for the rule where the a value is equal to 1. Again, the square root of the constant is the a value. So I would write 1 over a, but that's 1 over 1, so I'm not going to write that. I will move on to the arc secant part. The arc secant is the only inverse trig rule that has absolute value in it, so don't forget about it. Absolute value of u over a, in this case, is just x over 1, so I'll just put x, and then plus c. For part B, we have this 36 that has appeared in the numerator. By now, you can guess that I'm just going to take that 36 and bring it out to the front of this integral, leaving behind 1 over x times the square root of x squared minus 1, which looks suspiciously like what we had in part A. It just has a 36 in front of it. So guess what? We will take our answer from part A, arc secant, absolute value of x, plus c, and we will simply bring down the 36. For part C, we see that the 36 is now the constant of the denominator. That tells us that the a value is going to be 6. It is the square root of the constant. So we can still use the rule, which is a perfect match. We just need to put 1 over a in the front. So now we have 1 over 6. Arc secant, absolute value of u over a, which in this case will be x over 6, plus c. For part D, we see the 36 in the numerator and the constant of the denominator. Let's bring that 36 out in front of the integral like you do, leaving behind 1 over x times the square root of x squared minus 36 dx. So this is exactly what we had in part C, just with a 36 in front of it. So I'm just going to copy the answer that we had from part C. So we had 1/6 arc secant absolute value of x over 6 plus c. But because we have this 36 in the front of the integral, we bring that down. 36 times 1/6 is 6. It's the same as 36 divided by 6. So there's your answer to part D. For the fourth set of problems, we will look at a variety of integrals that have no square roots in them. Some of these will be inverse trig and some of them will not. So remember, if the degree of the denominator beats the degree of the numerator by 2 or more, then it's inverse trig. Otherwise, we use U-Substitution. In this case, the degree of the numerator is 0. The degree of the denominator is 2. Because the denominator degree wins by 2, we know it will be inverse trig. Because there is no square root and we see the addition sign, we know this will be the Arctangent Rule. So this is a perfect match, except that the a value is equal to 5. The a value will be the square root of this constant. By the way, I see in the rule, the way it is written, we have the constant plus the variable. And here we have the variable plus the constant. That makes no difference because addition is commutative. If this were subtraction, the order would matter. Anyway, the rule says 1 over a. So I will put 1 over 5, arctangent. And then we have u over a, which in this case will just be x over 5, plus c. So there's your answer to part A. Part B is different because we see this x in the numerator. This changes things because now the degree of the numerator is 1, while the degree of the denominator is 2. Since the denominator only wins by 1, that means we will use U-Substitution. Let's let u equal the entire denominator, x squared plus 25. That means that u prime will equal 2x. So we will do the substitution. We will end up with x over u. We let the entire denominator be u. And instead of dx, we write du over u prime, which is 2x. And then we notice that we have an x in the numerator and an x in the denominator. These will cancel each other out. The 2 in the denominator can be brought out to the front as a 1/2. This leaves the integral of 1 over u du, which leads us to a memorized rule. The integral of 1 over u du is the natural log of the absolute value of u plus c. Because of the 1/2 in the front, we will bring that down. But make sure you have this rule memorized. Substituting x squared plus 25 for u, we have the final answer. For part C, we notice that the degrees of the numerator and denominator are equal. For that reason, we will use neither inverse trig nor U-Substitution, at least not right away. Instead, we have to use long division. So we are dividing the denominator into the numerator. So we will set up our long division like this: x squared plus 25 divided into x squared. I don't know why I made it so big. So we have this. Then we ask ourselves, x squared times what will give us x squared? And of course, that answer is going to be 1. Then we turn around and do the distributive property with this 1. 1 times x squared is x squared. 1 times 25 is 25. And then we subtract. So when you subtract, you get 0, right? X squared minus x squared is 0. But then we have 0 minus 25, so that'll just be a negative 25. This is the remainder, so what do I do with it? I take the remainder and I put it over the divisor. So I have minus 25 over x squared plus 25. The expression that we see on the top of this division is equivalent to the original integrand. So I am going to rewrite the integral, making this substitution. So now we have this. I think this will work better if we split this up as two separate integrals. I also went ahead and took the liberty of taking this 25 and putting it out in the front of the integral like you do, instead of leaving it in the numerator. So the integral of 1 dx is just x. And there's my minus 25. I'm just going to bring that down. The rest of this integral is a perfect match for the arctangent rule. Just keep in mind that the a value is going to be 5 because it is the square root of 25. So the arctangent rule has a 1 over a in the front of it. So I'm going to have 1 over 5. And then we say arctangent. And then we have u over a, which in this case will just be x over 5, plus c. Of course, 25 times 1/5 is 5, because this is the same as 25 divided by 5. So this will be the answer to part C. For part D, the degree of the numerator is greater than the degree of the denominator. So I will definitely do long division. So we're dividing x squared plus 25 into x to the third power. So let's get started. We ask ourselves x squared times what will be x to the third power? And that's x squared times x. We turn around and do the distributive property. So I'm multiplying this x by both of these. X times x squared is x to the third power. X times 25 is 25x. And then we turn around and we subtract. So x to the third power minus x to the third power is 0. And then we have nothing minus 25x, so that's going to be a negative 25x. Once you notice that the degree of what you have is less than the degree of the divisor, you're looking at the remainder. So we say, take that negative sign and just put it right there. And then we put the 25x remainder over the divisor, which is x squared plus 25. Everything you see right here is equivalent to the integrand that we started with. So I am going to make that substitution on the next step. I went ahead and divided this up into two separate integrals. The integral of x is just going to be x squared over 1/2, x squared divided by 2, which I will just put the 1/2 out in the front. Moving on to the next term, I am going to do some U-substitution actually. I notice that the degree of the denominator wins by exactly 1. So that tells me that U-substitution should apply. Let's let U equal the entire denominator. So U will equal x squared plus 25, which means that U prime will equal 2x. As we make the substitution, we have the integral of 25x over u. Instead of dx, we write du over u prime, which is 2x. We notice that we have x in the numerator and the denominator, so those cancel each other out. We still have the 25 in the numerator and the 2 in the denominator. These can both be brought out in front of the integral as 25 over 2, which leaves behind the integral of 1 over u du. But this will be a memorized rule. We know that the integral of 1 over u du is the natural log of the absolute value of u plus c. Bringing everything else down, we have this. Substituting the x squared plus 25 back in for u gives us the final answer. You might also notice that I'm using normal parentheses now instead of the absolute value. That's because the x squared is always positive. Adding 25 still leaves it a positive value. So we no longer need the absolute value to guarantee that we have a positive number. It's fine if you leave the absolute value, but I'm just pointing out that it's not necessary. For part E, the degree of the denominator wins by exactly 1. When we see that, we think U-substitution. Let's let u equal the entire denominator, x to the 4th power plus 25. That means that u prime will equal 4x to the 3rd power. If we perform the substitution, we get the integral of x to the 3rd power over u. Instead of dx, we will write du over u prime. But u prime is 4x to the 3rd power. Then we notice that we have x to the 3rd power in the numerator and the denominator, so those will cancel each other out. The 4 in the denominator can be brought out in the front as a 1/4, leaving behind the integral of 1 over u du. But this integral is a memorized rule. We know this is the natural log of the absolute value of u plus c. We bring down the 1/4, of course. Substituting x to the 4th power plus 25 back in for u gives us the final answer. Notice that we no longer need the absolute value symbol because x to the 4th power plus 25 is always positive. Remember, if the degree of the denominator beats the degree of the numerator by 2 or more, then we use inverse trig rules, and that's the case here. In this case, we can tell that it will be the inverse tangent rule because there's no square root and it's addition. So to make this match the rule more perfectly, I need something squared, right? We see the u squared, but I have x to the 4th power. So I would like to rewrite this as something squared. While I'm at it, I think I'll just flip these around the other way to make it match the rule even more perfectly. So I'm going to write x over, I'm putting the 25 in the front, so I know that I need something squared. Well, that would have to now be x squared squared, because that has the same value as x to the 4th power. Let's not forget the dx. The u is whatever is being squared. So that tells us that the u must be x squared, which means u prime will equal 2x. If we do this substitution, we end up with the integral of x over 25 plus u squared. Instead of dx, we must write du over u prime, which is 2x. But then we see that we have an x in the numerator and in the denominator. These cancel each other out. The 2 that remains in the denominator can be brought out to the front of the integral as a 1/2. That leaves behind the integral of 1 over 25 plus u squared du. This matches the rule perfectly with an a value of 5. The a value is always the square root of the constant. Let's apply the rule. We need 1 over a, so that will be 1 over 5. And then arctangent u over a. Well, u is x squared, so I will go ahead and put x squared over 5. And then plus c. But let's not forget that we do have this 1/2 sitting out in the very front. So that is still there. So this is the final answer for part F.